Ladies and gentlemen, welcome to the VMware Networking and Security live stream. We are back. Sorry, we were going to start at 2:30, but we had a few little technical difficulties, so not a big deal. We've actually passed through it now. We're good to go. We're back up and running. So anyway, we're going to start off. Today, the show is all about NSX networking and the basics. So what we've been doing the past couple of weeks with Paul Mancuso and doing some of the work on understanding networking, we got a little bit in depth in some certain topics, and we kind of took a step back and realized that maybe we want to take a little bit more of a simplistic of approach of how these things connect to your enterprise network, how the edges work. We've talked about TEPs, we've talked about a few different things, but let's get a little bit more clarification on that. So without further ado, I'm going to bring in my guest, Mr. Paul Mancuso. How you doing?
Very well, Andrew. Good to be here. Sorry for the delay. It's actually my fault, folks. It was my system. I blame it on a particular OS, I suppose. But whatever it is, it appears to be rectified, or at least so we hope.
No worries, no worries. You know what? You sound good. We got over the audio issues. I think we're all set to go here. So yeah, you know what? Let's start off. So, like I did in the intro here, Paul, we kind of, we went a little bit more in depth on some of the other networking topics. And you and I were discussing last week of maybe we should take a step back and have just more of a simplistic discussion of how all of these things connect. I think there's a lot of questions on, how does it connect into the enterprise network? We talked a little bit over routing protocols before, like BGP and OSPF, but let's start super, super simple. So, I mean, really, how do we actually connect NSX into our enterprise network?
All right, well, we first should then delve into more or less the physical infrastructure, because obviously one's going to exist. As much as we'd love to sit here and talk about NSX providing all of your networking needs, there's one particular element NSX cannot produce at the present moment, unless something gets changed in spatial time elements of some sort. NSX cannot produce the physical fabric of itself. So it will always exist. And I think maybe a good starting point for that physical fabric discussion is, what would that makeup look like? And then we can go from there. What do you think?
I think that sounds like a great idea. How about we start delving into it?
Okay. Well, your physical fabric could be one of a variety of flavors of options as far as what its makeup is and its connectivity. We don't care so much about the actual vendor per se. We're looking at more or less the makeup of the protocol configuration and its encapsulation servicing of whatever it's using, like VLAN versus VXLAN in the fabric, and things of that nature. And then what it will utilize from the server face, the server interfaces, so the infrastructure side versus the fabric side. So the fabric side would be the side of the switch that intercommunicates within the fabric itself, whether you have a traditional access distribution core or you have a newer leaf spine. And by the way, those would be our two basic structures of that fabric. And let's talk about both of those, right?
Let's actually get into that. So really, first off, Paul, like, you bring up two good points. So like in networking, we've always had this, we've had two really big disciplines, I would say, is you have your core distribution access. And now a lot of times you see in data centers, a cloth architecture, a spine leaf, whichever you would like to call it. Let me ask a simple question. Does it even matter which design you have, and does it influence how we're going to design NSX and have it connect in?
Well, I think how it would influence how it would connect in is that when we look at setting up this switch infrastructure, and we're just going to draw a very simple one. Normally, I just draw a flat line for it because we only care so much about the VLANs that face the infrastructure, the servers themselves, the host. What is built within the physical fabric, what its makeup is as far as its structure above it. All right, we'll say above it this time, because normally I would just draw it down here and we draw our virtual infrastructure here. Since today is going to be a focal point of the physical connectivity, we'll draw it from a top-down physical, and then the virtual will be down here. All right.
Sure.
By the way, that's traditionally the way you should think of it anyway. We draw it the other way around when we do a lot of our VMware diagrams, because obviously we're focusing more on it. So we put that on the top, and the physical infrastructure is transparently operational from the bottom's perspective. But it's a north-south perspective. So your physical technically would be the north side of your communication. NSX would typically be considered the south side. Everything should sort of end in it, right? It's where the communication will come to an endpoint of some sort. right?
Yeah.
With in the virtual, and then there's an east-west communication of sorts. So let's talk about that physical infrastructure before we go any deeper into that area.
Sure.
All right. So in there, I'm going to draw just a simple access, distribution, and core. This would be our prototypical legacy style setup. And you would have 3 layers. Now, remember, if you're a very small environment, you might just have some access switches that does everything, right? I mean, years ago, when I'm sure Andrew, it might even be before you were born. Okay.
Hey, hold on there. I'm not that young.
Well, today's my birthday, so I'm 59. So
I forgot about that. Happy birthday.
All right. But let's put it this way: before you actually were able to actually say switch. Okay.
All right, fair enough.
All right. That wasn't a word in your vocabulary lingo. Let's put it that way.
It was actually my first word.
Up...
You don't know this. It was my first word.
Okay. Well, then your mom would be pretty upset, I'm sure. So the networks that we would typically set up back then would just have a couple of switches inside of a closet. There'd be no routers that would be part of the actual infrastructure itself. There'd be a WAN connection, of course, that would get them out to whatever wide area connection it is prior to the internet at that time. But at the same point, there would be a very small, in the closet network was literally in a closet. Okay. All right. And then, of course, data centers became a thing as enterprises grew. And technically, all large enterprises always had some data center of sort. It was the smaller ones that I was referring to earlier, when that much of us back in the late 80s, early 90s would get a lot of, or cut our teeth on as far as networking chops. So anyway, as we built into the data center, the access, distribution, and core, and this would typically be switched or bridged in the earlier goings, and then switched, of course, as time went on. So the connectivity here was very simple. You would just have essentially a switch connection here.
And of course, as you're drawing those out, just to point out, with those being all trunks and the layer 2 being passed all the way down, we're dealing with spanning tree. We're dealing with those normal things that we would have in the networking world.
Right. And I was going to just draw the physical links first.
Sure.
And then we'll get into the protocol makeup in a moment. Now, and then above it, well, there could be a mix, depending upon the environment, of switched or physical interface routing. Let's deal with what would probably be more so in many of the environments that we would see today, that we would see a lot of people, usually going to some type of switched infrastructure here, but with routed SVIs for interconnectivity. And the distribution layer would also typically have a connection between them. And we would see the same here, so that we could have failover of, let's say, the downstream port interfaces, but we could still connect in and out of each and every one of these through a variety of redundant mechanisms.
Sure.
But that was also one of the fallacy, or one of the downsides of this environment, is that sharing load among these was a difficulty in achieving. So you'd have to use a variety of first hop routing protocols, for instance, because actually, before we get into that, let's actually talk about what you said before. This would be our switched architecture. It consists of spanning tree makeup, so that we could make certain of where our root bridge was and things of that nature. And we typically want the root bridge for the VLANs to be shared among here. And then, of course, the failover root bridge would be the other distribution switch.
Yep.
All right. And in that case, then you'd play with a lot of the characteristics of the VLAN values. These switches here that would reside in the racks themselves, obviously these are going to be racks someplace as well, but these could be end of row, middle of row, that kind of thinking, and how you actually cable it, that's not our concern. All right. Sure. But there would be a variety of architectural ideals that would make it suitable for your infrastructure to best utilize a wiring of some sort. So the TORs that we would have here, they would have, of course, switched connections into the host. And we'll get a little more specific about these later.
Okay.
All right. And these would be where you would, in the early days, might actually not have anything other than just access VLAN ports until trunking became more the norm, because we were sending more than a single VLAN inside of a ESXi host. In the early days in the ESX host, we might actually have 5 to 7 1 gigabit NICs, and each one would just be a dedicated VLAN. So therefore it'd just be an access port that would be going to, and you wouldn't care about what VLAN value was actually on the port group of the vSwitch and ESXi, because only one VLAN was coming into it anyway. And therefore, whatever it is, that's where your home was. So let's talk more then about how it actually evolved toward the end. And we say the end, meaning that you may still have this environment. So we're not sitting here disparaging it, because if it's lasted this long, good for you. That meant you got a lot of money out of your world. All right. But this is an old world from a legacy standpoint, because it suffers from a handful of architectural defects, if you will. The first one being the issue of how do we actually engage a equal cost usage of the distribution links without having to go through, a ton of hoops as far as how to make that occur using what we call first hop routing protocols, right? So their HSRP was, of course, Cisco's, and all the other vendors technically had some proprietary extensions before VRRP, Virtual Routing Redundancy Protocol, became the de facto adopted standard for first hop routing protocols. So that way then I could actually put a virtual bridged or virtual gateway value and then layer it across both of them. So that way then I could plausibly at least use them for active standby. And then depending upon the vendor's proprietary take after that, might actually be able to make them equally active at the same time. And there were ways to make that occur. But again, that would be vendor specific at that point, because that's not part of the protocol itself.
And we're not even touching upon virtual port channels and the NXOS or anything like that. We're not like, this is still, we're talking about old school stuff.
Old school, so straight links, no, and if we did have channels, this one might be, each of these links that are drawn here might be more of a logical link with 2 physical or 4 physical channeled links, because obviously redundancy for each of those connection, adding additional IO and an additional ratio of your fan in and fan out, depending upon the nature of your requirements. Because in this world, much of your transactions was likely north-south.
Yes.
East-west didn't begin to take over until applications began becoming a much more complex beast, and they would become a multi-tiered set of services versus either just a single endpoint or a client server type of application where you just had an intelligent browser. The back end was maybe a front end responder to the web service itself and a back end database, or just a front end of proprietary front-end application interface with a back-end database, but technically still just a 2-tiered app of some sort. And sometimes they were multi-tiered only because they were just very custom-oriented and very vertically oriented in their own prescriptive manner. But as applications became essentially much more complex, back around the Netscape days, right, we started seeing the multi-tiered applications, and we started seeing some east-west communication begin to take a higher prioritization as far as IO consumption within the fabric. And we mean by east-west, if we were to start drawing in a handful of hosts here with workloads on them, and then we should probably draw this a bit more prescriptive so that these connections would be more along the line of what they would truly look like, right?
And just remember, while Paul is drawing this all out, if anybody has any questions or comments, feel free to put them into there. I'm constantly monitoring it, and we will answer questions live.
All right. So we have a workload, and it's like if you have to have a day that just nothing goes right, this is definitely that one. Okay, so here we go. So we have a workload here. And what we'll do is we'll draw them as if the workload colors are essentially meaning they're on the same or different network. So this could be, let's say, a different network.
Gotcha.
All right, so the orange VLAN and that's supposed to be yellow. As you can see, it probably looks green to you folks out there. Okay. All right. So the way these two would communicate is they'd have to get routed. Well, their SVI probably lives somewhere in this realm up here. So again, we'll just keep it simple. there'll be a yellow SVI here, and there'll be an orange one. And let's just assume there is some type of redundancy allowing both of them to be available on this distribution. They could be active standby, they could be active. We truly don't care, because for the purpose of this conversation, it's not relevant. It's what's relevant is that the termination of those VLANs is here. All right. And therefore, in order for these two to communicate, it must get to the distribution layer before it actually gets back to its destination.
Yep. So basically traversing through the access layer, going to the layer 3 SVI on the distribution layer, doing the routing through, and then coming right back down.
Correct. So in this case, then, why is this a concern? Well, this means your communication is almost all going to be, you see your communication here is beginning to start to resemble some east-west, with the distribution layer playing a major portion of the activity as far as concerning what communication is going to be permitted. So we could start putting some ACLs. We could even layer off firewalls off the distribution layer so that we could begin to craft some stateful firewall management of applications, probably more macro segmented. So we might not do it between workloads within the same app, but we might want to say this app, which is doing some credit card stuff, can't communicate with this app, which is not, something to that nature. And we could begin to distinguish things prior to some of the security concerns becoming a bit more micromanaging as far as what can be permitted to communicate. But
this was a big concern back in the day from a design perspective, because it was, a decision over, are you going to put your SVIs over on your distribution layer? Are you going to put it on your core? If you wanted to have lateral security in some way, or east-west, you're only going to be able to put it between the layer 3 unless you want to start working with private VLANs. And we know that as those you add more of those complexities, it becomes harder to be able to troubleshoot, and it's operationally a little bit more taxing.
Correct. In order for these then to communicate externally, obviously they must go through the core, and the core could obviously interconnect them depending upon the nature of where you would like to intersect it with various wide area networks, or with the internet as it became obviously much more relevant. Those types of decision points would become, because the distribution point would become a logical place to put some of that, and the core being in another area where inter traffic between the data centers themselves. The distribution could be distributing traffic for a variety of other reasons, for campus networks, things of that nature. All right, so they obviously had their own specific purposes, and you would designate what those purposes would be like for you manage your traffic directions and what was desired for communication downstream, and to manage what was allowed downstream into these particular endpoints. And in some environments, the only downstream management of sorts would just be that perimeter firewall and some measly ACLs at the switch or the router, as you noted, could be placed upon those routed endpoints. All right. So that's our basic older style network. This network still could exist today with some minor updates to it. Minor updates would be for highly available connectivity to improve upon the fact that this is a pod network. Your distribution network really can't take another distribution switch, because it doesn't do anything, because none of the proprietary extensions really allowed at leveraging a third or a fourth or a fifth switch at there. Same with the core. So the only means of actual scaling it was to craft a whole new pod architecture. So you would see multiple pod architectures, and that's where your core comes into play as far as managing traffic between each of those different pods. And then the distribution being a means of maybe service-oriented service of offerings of sorts. So DHCP, DNS, SS, your syslogging, all of those kinds of things, and firewall servicing of some sort, load balancing, et cetera. All right. So this becomes your services layer. This becomes your interconnectivity layer and things of that nature. Some mix of that, of course, because there's a lot of hybrids of that. But the issue still being, this architecture would eventually exhaust itself in some way. You'd run out of ports because of IO requirements. You would have multiple channels coming in to each of these various links between each of them, maybe even between the switches themselves at the same layer, because if you would lose, let's say, both of these links and these needed to get in and out, you'd want to have that highly available traffic that could permit traffic still to and from it without it having to essentially kill off all of the traffic going into its one switch downstream. So it would still lend itself a little bit more of highly available connectivity options. And then you'd have a variety of protocols that would allow you to determine what links were available upstream and downstream on a switch so that it would know which ports to leave open and which ports to close off in case they could black hole traffic. So it could
I
be
mean, not
some
only that, I mean, remember the days of, if you were in, a smaller kind of data center, and depending on the hardware you had, you could have a maximum amount of spanning tree instances that you can have. You only have so many VLANs that you can create. So as you would start to expand and create more and more and more of these, you would reach limitations of the, of the enterprise network and the switches that you had.
Correct. Yeah. So that is true. Not to mention the processing overhead, because we're talking very old CPU architectures in a lot of these. They couldn't just stick in the latest hotness from Intel or AMD. And a lot of them, and some of the times, like Cisco would use its own proprietary CPUs for some of their switches themselves anyway. So they would get obviously some silicon vendor to craft those for their purposes. But the idea being is that you're right. They were limited in how much they could have processing overhead. All right. So anyway, let's get then to what we care about today. So today would be is that we'd have VPCs, or we would have multi-lag or multi-chassis ether channel, where these links could actually be, redundant, so that this guy thinks that when he's talking to these two switches, he sees it as a single switch. So we would
essentially fooling spanning tree. It's fooling it into thinking that it's just one big logical spanning tree instance or switch that's there.
Yeah, and the same thing for here. We put VPC links here. All right. Now, in Cisco's VPC, spanning tree still operates underneath the covers. It's required. In fact, if it were to fail, it would actually fail the VPC itself. There are ways, of course, to deal with how that would operate, whether it actually causes some of the extreme failures as the protocol matured over time. But the issue being is that it was still there. So you're still operating with L2 concerns of the legacy days as far as manipulating the protocols underneath the VPC traffic or the multi-chassis ether channel connection, right? Multi-chassis ether channel. All right.
Yep.
All right. Therefore, and by the way, there was no standard for those. So as far as I know, I think there was a provider standard of some sort for multi-chassis ether channel of some sort, and that depended upon some protocol operational servicing that you would use in the service provider environment. But there was never anything for the enterprise, as far as I know. And the one in the service provider, I'm just recalling something that I remember seeing. I don't never know if it ever got ratified. I remember just reading some draft of some sort. When you fly a lot, you tend to read a lot of that garbage on planes, because I could never sleep on a plane. So I would just try to fill my time with reading stuff that seemed interesting at the time. These links that we're running these VPCs then would, of course, offer us the ability to have redundant or a better cost usage or bilateral usage of each of the links that were going into and out of the switches themselves. But again, we would still exhaust the capability of this switch architecture at some point, and we still didn't solve the issue of scaling it beyond a certain capability based upon the ports and the amount of I/O that those ports would afford us to consume. Because as we stated before, if we needed several links going to each of these, there's only X number of ports that are finite as far as usage going downstream, and we'd have to keep some for upstream, and et cetera. All right, so this is one. So here then, let's talk about what we would use then, what we would see from an NSX perspective. And technically, this part here is you're going to note, it's going to stay the same across the board. All right, or to some extent, there's a high level 10,000 foot view that doesn't really ever change, which is why we say we're agnostic to the switch infrastructure. When we say we mean NSX being the we here.
Yeah.
So the VLANs here are still going to be those same few VLANs. So we talk about what are those VLANs? What are the necessary VLANs for the infrastructure? So, NSX required VLANs. And even then, the word requirement here is a bit, we're taking some liberties with. The one the one VLAN we have to have, is going to be management. We're not going to be able to get away from anything without management. So management is definitely going to be one.
Sure.
Right, because management is used by NSX and vSphere, of course. Management is used by vSphere to manage the vSphere host, and it's used by vSphere also to manage the control plane configuration of the distributed switch or vSwitch, and of course the operations of the host itself. And for NSX, NSX uses the management link for its management, of course. All right, assuming you use the same physical link or logical link even. All right, but you'll use NSX for management of it, and it also relates control plane knowledge too. So in other words, lookups to the NSX manager for endpoint resolution, for TEPs and things of that nature, and for route updates and things. There's some in the older NSX VLAN one, there was actual lookups into the control plane for the routed information and things of that nature. And then for NSXT, the latest one, or we're now just calling NSX, we now use it, of course, to relate control plane stability information, and the control plane protocols operate in a slightly different fashion than the way NSXV operated as far as routing goes.
And they're not having to be on the same layer too. They can be layer 3 separated apart as long as you don't have really a firewall device that could be blocking the necessary ports. It does not matter. They do not need to be on the same layer 2. That is not a requirement.
Right. Now, it's the other two that are technically not required. The next two, I should say.
Sure.
vMotion, you don't have to have it. It's just foolish not to. So your vMotion port, and then your IP storage port. All right. Obviously, IP storage is if you're using IP storage from the VM kernel, right? The actual kernel of the system itself for performing a software iSCSI or a software NFS version usage of it, or vSAN or some virtual SAN of another vendor, whatever. So you'd have an actual logical link for IP communication for storage. Obviously, vMotion is vMotion. I hope we don't have to explain that to our audience. All right.
I think we can move on.
Yeah. Therefore, then the fourth and final one is we're going to call transport. Okay. All right. That provides the network virtualization communication from the tunneling endpoints of each of our hosts. So each of our hosts are going to have a tunneling endpoint within them. All right. So that's going to
also be what we would call a TEP, a tunneling endpoint or a TEP.
Or a TEP. And we'll put that in green so that we can note its significance. All right. So it's the TEP. And so for NSX, the TEP traffic now becomes this. So instead of this orange and green communicating up to here for its routed communication, it now just tunnels all of its communication through these TEPs, because the routed traffic will actually occur in the kernel. So we'll have routers instantiated in the kernel. And that goes back to our earlier discussion of how the distributed routing occurs inside of an NSX. So go back and look at a previous one. But so in order for this to route to this one, technically it routes on the originating host of the source. And when it gets into the TEP, it's an overlay communication. It's a tunnel. It's a virtualized communication using the physical fabric as its transport, hence the term transport.
Yep.
And therefore, it only requires an L2 hop, assuming each of these TEPs are on the same L2 domain. Okay.
So that's pretty significant there, because what you're basically saying is, instead of in the old way, me having to go through the access layer, and then in this case, we had the SVI living on the distribution layer, instead of having to go out there and then almost like trombone right back into it, and I know that's not technically the right term in this, but we're going to go with it. You're just literally sitting in the host, and then it'll route. If it's on the same host, like let's say you had two orange that were sitting on that far left one, it wouldn't even have to journey outside, even if they were on separate subnets. Let's say that you had the orange and the green, it looks like, even though it's yellow, sitting on the same host. It's not having to traverse outside to then do that VLAN hop, that layer 3 route, switch. Essentially, it's staying inside the host, and all the routing is happening inside of it.
Correct. So the switch, the mapping characteristics of these two communicating and these two communicating would look the same. They would simply go into the local kernel of the system itself, and NSX would provide the distributed routing right there on the host, so it never leaves the host for these two to communicate. And the same with this one, even though these two are switched, logically switched, and these two are logically routed.
We have a fantastic question. What piece of software or hardware is responsible for the encapsulation of Geneve on the TEP?
Well, that's the NSX itself. That is NSX providing these VMware installable bundles inside of the kernel that provides the magic of how NSX operates in the kernel. And we refer to that as near line rate, because obviously it's not a physical line, but we're operating in a distinct memory ring 0 inside of that kernel to give us extremely high efficiency at movement of the frames at almost a physical perspective capabilities. So that's why we nickname it near line rate. Sometimes we'll just say line rate to save it, but it technically should be called near line rate because all right. But here's the beauty of this though. And this is where we actually exceed anything close to near line rate. These two communicating in here are not going to communicate at near line rate. They're going to communicate at whatever the capacity value that can be pushed in the IO of the internal host itself. And you'll have Samuel Komu at various VMware or VMworlds in the past and VMware Explorers. He'll have demonstrations showing you live demonstrations. Mind you, he's a very risky man to sit up there and do live demonstrations of IO capability of NSX. You got to give him props for that. And
very brave.
He's done it. Yeah. And he's showing you where you're exceeding 120 gigabits in the course, the more modern host, right? Obviously not the host 20 years ago or so. But so in other words, you could have 10, 25 or 40 gigabit links on the physical, et cetera, or even one, but in the chassis itself, communication will be running at whatever the chassis IO capacity is, which has nothing to do with the NIC, even though the NIC in here is some VMX Net 3 adapter or something like that. That's irrelevant. All right. It's obviously it needs that adapter to get that capability. So you have to put the superior adapter that VMware prescribes for its NSX usage in that environment. And then once you do so, you'll achieve these exceedingly ridiculously high performance rates on the host itself. Now, obviously, once you pass the host outside the host itself or anything whatsoever to hit the physical fabric, you are now constrained by physical limitations, of course.
Now, interesting question here. Can that be encrypted? So I would say from inside the kernel itself and just going between the two segments that are inside of it, that doesn't need to necessarily be encrypted. But I think he's really Mohammed wants to focus on if it's going from host to host.
Well, we played with the idea of doing an encryption within the transport zone at one point with NSX-T. All right. And with NSX-V, the earlier flavor of NSX, and NSX multi-hypervisor, neither of those two ever had an encrypted one. NSX-T technically toyed with the idea for a limited time. I know it came out when I was an employee of VMware at the time. I'm still an employee of VMware, but at least at the time of this recording. When it came out, I can't recall if it was ever trucked to technically production. I just don't remember. But we did toy with the idea of doing an encrypted channel.
They did. And I think that feature was deprecated at one point because of it just wasn't really being utilized.
Performance wasn't the greatest. We should be honest.
Performance
because the offloads just weren't there yet. The NICs just weren't mature enough for offloads.
And look, that might come back in, when you start talking about, smart NICs and things like that. That could be, something that's out there. But for right now, no, in transit, it would not be encrypted.
And by the way, that's something they should look at. Take a look at what we're doing with Smart NICs. Smart NICs is going to give us that acceleration of a hardware like ASIC on the NIC, so that NSX will be able to afford a variety of features, and encryption is definitely being looked into. All right. So anyway, then the answer is no today, though. So I apologize for not being able to offer it, but can't do what we don't do yet. All right. So going then to our discussion, because we're going to be able to actually change this rapidly to the next ones, because it's going to be rather easy, because we've kind of done the same discussion as far as communicating between the host or between the workloads on the same host, between workloads on different hosts. The only distinction that we would have at the pod architecture is extending the VLANs, which, by the way, was always an issue, even with vMotion and HA and things of that nature throughout and pervasive throughout the environment, because the limitation of number of VLANs you're permitted to obviously operate within a pod was always going to be that 4,090. And then even with a Nexus, you really were restricted to something much less than that, because there was a lot of reserve VLANs and things like that. And I'm sure the other vendor switches had their restrictions, but nevertheless, you're that 4,000 level someplace, right? And extending it was also an L2 issue, because you would have issues with broadcast domains and things of that nature. If you had a lot of multicast that was L2 versus L3, there could be concerns as far as how much IO was being proliferated throughout the environment, could create some storms if it wasn't properly manicured, etc. So you could see that this world had a series of non-ideal issues. All right.
Well, yeah, I mean, look, I mean, it doesn't even have to go that complex. I remember in days when I was working in data centers where, we went toward an architecture where we wanted every single rack to be, a layer 3 connection, from the distribution maybe to the top of rack switch. And you would have your VLANs in there. So that way we wouldn't come into the, running out of VLANs over the overall data center. But then the minute that you had somebody go, well, I need this workload in rack 1 and you don't have enough compute, so I need it in rack 2 and I need them to be on the same layer 2. Now we had a problem.
All right. Now, before I begin erasing things, is there something we're missing? Or any other questions on this? I mean, there's a plethora of different types of topics we could go through, but I think the main concern was how do we actually graph the communication of the host into the physical infrastructure? And we noted that there would be these VLANs. They could, I guess we should probably just then go one step further. These VLANs could be rack based. And then the 4 VLANs that are on that's rack 2 versus rack 3 versus rack 4 could be 4 entirely different VLANs. Because maybe we won't stretch them, or maybe we'll do it based upon half a row versus a full row, et cetera, or maybe a few racks versus a couple of racks, whatever. There could obviously be a series of hybrid decisions in there, but realizing the moment you're stretching that VLAN, you're causing quite a bit of operational overhead in doing so. And so it just wasn't usually a preferable style. So it was unusual to see that actually drawn out in that such regard. These were usually then separate VLANs just because of that, which also meant that the scope of your vMotion and HA would get, of course, severely restricted to only a series of racks, et cetera, within your infrastructure.
Yep, and Mohammed, he's saying that OTV could have solved that issue, and you're right. OTV could have solved that issue, but also OTV had its own, especially when it was come between data centers. You had, the threat of tromboning traffic, and you had to be very careful with how you configured it. It added more operational complexity, and it's one of those things that I know that OTV was not greatly, especially in the very beginning, adopted very well because of its complexity. But I think over time, people have become a little bit more comfortable with it. But no, we love the questions, Mohammed. Keep on bringing them out. I mean, we're liking it. We're liking the comments.
But oddly enough, Mohammed brings up a very interesting point. I don't want to spend too much time on it, but I will just make a couple of comments. OTV was, of course, meant to be a DCI interconnect so that I could stretch L2. That was it. And of course, it could do it between campus localities and things of that nature too, within intra-campus, I should say, right? Or a metropolitan area, et cetera. But interestingly enough, the main uses of it before it was trusted for that DCI L2 extension, because it's obviously the moment you extend L2, you've just extended your problems. All right. It was used intra DC by very large companies. So Mohammed is correct. That's probably why he maybe mentioned it, because maybe he's remembering something that was done within an organization he worked at the time. But yes, it was actually introduced very often in the early stages as an intra and our intra-campus or an intra-large DC means of L2 extension, because the pod architecture simply became, and they would build out a new pod and they would want to extend that L2. They could definitely use OTV for that. Okay, anyway, all right, that's all good. So I think we've covered this. We're good on this?
Yeah, I think we're good. I know there was a question that was asked about how the edges are going to play into this. So I've said we are going to eventually touch into the edges. We will touch into the edges a little bit.
All right. So the edges, let's just say we have some edges over here. So this would be a cluster that's strictly edges. And these then would obviously connect upstream. And we would use a series of VLANs here for the intermediary communication for the SVIs of the host themselves and the edge virtual machines that would be operating on a BGP nature. Now, we would have to note too that the TEPs, as we showed here, are actually inside of the hosts. Well, the TEPs for the edges is actually in here. So there may be TEPs here, but these would be for the workloads. Correct. The TEPs then for the actual edges east-west communication, so that if this wanted to route out to something outside the environment, it would actually send it. It would go upstream. It would go up to that distribution layer, come back down to the TORs. And then depending upon the nature of HA or ECMP, active-active architecture of your edge, it could use one of these edges so that it would, of course, hit the TEP, and then it would route back out and then go, of course, back up. And then it would hit some outbound routed connection
Correct.
for wherever it needed to go, or maybe back to, let's say, something that was all virtual for multiple layers and hidden a database off of another switch, and the database being a physical system in
Yep.
some of the early stages of the infrastructure for NSX.
And just to let the people know that, this could actually be not only virtual, but it can also be a bare metal host as well. So we do have bare metal edges. We traditionally, at least with most of the people that I see a lot of VM based edges that are out there. So perfectly viable, perfectly still use DPDK, all these things that are there. So, I mean, still very good and still very flexible. And, you can deploy more if you need.
All right, then. All right, so we've covered there's some basic elements of the edge, but the idea being that we would have BGP, eBGP over here. We could use OSPF in the early NSXV, and NSXT eventually adopted its usage as well, but we use eBGP mostly, although you could also use IBGP if you wish. All right, and of course, static routing was always afforded option. It's just that static routing had issues on the early stages of ECMP capability. All right.
One of these days we'll have to go into a in-depth discussion of eBGP, IBGP, and OSPF, and which one
right,
we can go have a discussion about that.
Right. All right. So we're all good then with this?
I think we are. So let's, we'll go into the next step of this.
All right. So why don't you start setting the stage for that as I go ahead and get this going? We're going to start talking leaf spine, right?
Leaf spine. Okay, so this is a Kloss architecture of pretty much of what you've heard of, and a little bit different than what we've been dealing with the core, distribution, and access level. These are all routed links that we're going to have. Normally, a company could be starting to talk about their own style of VXLAN that they could be setting up within it, and we're going to talk about with the Kloss architecture how we would be connecting the rest of the NSX fabric up to it. I like to refer to the edges just as a side note, and what we were talking about them as the edge node is almost like the onboard or the bridge that goes into the NSX fabric. It's your main way to go in and out north south into it. So that's your highway. That's your way of being able to get in and off of it. Actually, Muhammad, you just had a question. Perfect. Can you explain traffic if there is an edge node hosted in the host that is prepared for NSXT? So essentially, having an edge node that is on a host that is prepped for NSX. I don't normally recommend putting an edge node onto a host that is prepped for NSX. We usually like to actually have a separate edge cluster.
No. Yeah, we do. The transport nodes today are now considered to be a good idea to be prepped for NSX for transport nodes, and then we'd run NSX. And here's the reason why. Starting with, I can't remember which flavor of NSX, but with flavor of NSX we have available to us. But in the past, we would run the edges without having to prep the host so that you could save on the licensing of NSX. Sure. But we now prep them because now we have a series of metrics and other troubleshooting tools that cannot be used unless that host is a transport host as well as an edge. So therefore, we now fully recommend and support. At this moment, we're deprecating the old way of doing it and fully support the idea of making certain that you always prep your hosts, all of your hosts, whether that's for compute or it's for transport of any sort of type. Okay, but edge should definitely be at this point done so.
Yeah, okay, well, look at that. I got to update myself.
Yeah, and when I say newly, it's newly from like a couple of years ago because I believe it was in the 3X train for NSX that we now started offering that ability to troubleshoot these. And that unfortunately that troubleshooting is unavailable without it being prepped, not because we want to force the licensing, but obviously it's the way we can shove all of that goodness of NSX understanding from an operational perspective into the kernel. And it's just too difficult to try and just manipulate it without that. So therefore it just became too cumbersome. The idea was just go ahead and prep the entirety of the host itself, run your edges on it. If there were issues that can be caught with the tools that we now provide inside of NSX for visibility, for connectivity, for firewalling, ACLs, and things of that nature, that could all be caught by the NSX management itself through some means, and therefore then operational ease is attained by doing that one meager thing. Obviously a little pricey, but one meager thing. Okay.
Yeah, and I don't believe that the traffic is going to be any different in the case of deploying
No.
the edge node, because essentially you're going to be still creating a VLAN back segment that goes off into your underlay network of some sort, your enterprise network, and then you're going to have your overlay transport zone that you're going to have connected to it. So that really the traffic going to the VM and in and out is really not going to be any different from if you had it on an unprepped host. You're just saying now we're getting more visibility with the VIBs being installed on it. We're getting all those metrics.
Right. Now, we start talking about a leaf spine architecture now. So that's our
Okay.
cloth-based fabric, as you mentioned before. Now we have a handful of other ideals. Now we can still draw, of course, a minimal of 2 in the spine.
Real quick, Paul, while you're drawing that out, he had one more question. Does the packet go out the host interface and come back? Only if it has to encapsulate that packet in some way, shape, or form to leave the current host that so if it's going to reach a workload that's outside the current host that the edge is on, then it would have to encapsulate and make it go out. Or if it's going out to the enterprise network to then lead to go into a workload that is not NSX prepped or not on the NSX fabric.
All right. So let's actually just deal with that one real quick. We could even draw out, because we covered that just a moment ago in essence, but it may not have hit specifically the ideal that Muhammad had in his mind. So let's try to make certain that we're not skipping over anything that he may be thinking differently than what we have stated.
Sure.
All right. So this would be our TEP. Remember, the orange was our TEP. So the orange is our TEP. Okay. All right. And if we have 2 workloads then on this host, we'll go back to our same set of virtual machines. And we'll keep it very simple. We'll keep it with just 2 logical segments. All right. I guess I probably should have used something different, but obviously I'm going to run out of colors here. And if I use some of the other colors, they don't show up so well. All right. If these 2 communicate, or these 2 communicate, it never leaves the host. Yep. There is no necessity for it to do so. All right. Obviously, there being no interceding of a load balancer of some sort that's elsewhere, or things like that. But if they communicate, they're their destined endpoint by the IP packet itself, right? Then they are going to communicate without leaving the host always. All right. And they're going to get
routing's locally on the actual host itself.
Right. Routing or switching. Correct. Right. And in an NSX environment, the beauty is you're technically a leaf spine architecture by logical IP as well as logical interconnectivity itself, meaning that nothing ever hops more than a single distributed routed segment in order to get to its endpoint. All right. You're always a single hop from whatever you need to communicate from logically from the workload's perspective, as far as whatever its next destination in order to get itself out of the environment, or within the environment, because the way it is here, since the TEP, we only allow a single layering of the TEP, with the exception being is you might have multiple T0s or something to that effect, and of course the T1, where you start. So as you ingress or egress into the environment, that being the exception, I'm referring to communication that is strictly encapsulated and is between workloads that are not communicating into or out of the edge. All right.
Yep.
I think, Muhammad, does that take care of your question? I just extended it with that last tidbit of info. So I hope that.
Yeah, if we weren't clear enough, Muhammad, feel free to add on and we'll be happy to answer. All
right. Now in a leaf spine architecture, let's go back up to the switch architecture. In the leaf spine architecture, we have essentially 2 major paradigms. All right. We have an L3 physical interface routed architecture we could do. You could still use it logical, I suppose, with switched interfaces, but you would do an actual routed architecture only. All right. So there's nothing else in here that's required. This is all just routed networks. And notice that the links are drawn in a specific explicit manner here. There's no requirement for links between the TORs themselves as well as the spines. Everything communicates to the TORs through those links. And this allows you then one specific value option, and that is now I can just add, and oops, that's that bad one I had from before. All right. I can then just add another one and notice what I get. I get the additional bandwidth and the use of this other spine so that I can add more fabric IO for my fan in and fan out ratio to the infrastructure host downstream of the TORs.
Yep.
This affords me a higher scalable environment, obviously a much more highly available, because now I have 2 that can die out of the 3 on the spine and still afford all communication without interruption. IO obviously might be a bit impacted, but the obvious nature of availability is met, as well as I can scale it. Almost, I wouldn't say linear, but it's a near linear fashion, right? I mean, you are obviously adding more.
And one of the things I'm noticing here is, just to highlight on it, we're not talking about using spanning tree here. These are layer 3 links. We're using ECMP, equal cost multipath routing. We're not having to concern ourselves with port channels in this case or anything. We're really dealing with, well, I mean, you can have port channels, but
Right.
But what I'm talking about is logical routed layer 3 links, and using ECMP is the main way of being able to distribute traffic between them.
Right, and you could use OSPF, or you could use BGP as your routing protocol. If you use BGP, you have reflectors from the spines, etc. So you could get that. But here's the thing: the physical nature. Again, let's remove anything that's being used with NSX downstream here.
Sure.
There would be no L2 extension here, right? I mean, because the L2 would exist only at the link themselves, because there is no interconnectivity. The only way to get L2 between these, obviously, would be if you were to do then a multi-chassis ether channel of some proprietary extension. So if you were to do VPC, all right, then at that point, then you would have a requirement for this link to exist, and you would have your VPC links downstream. All right. So I'm not suggesting you won't do that, because it obviously affords you some nice magic. We will assume at the moment not, just so we'll stick with the actual standard versus the extensions that the vendors themselves can, of course, add to it.
But definitely at least acknowledging the fact that it will be out there and it is in the wild.
Right. And then I think now, from a routed nature, then the only way then we're going to get extension, if we were to use a routed, but it would be extremely simple. And here's the pure value of this. I don't need the ability to extend L2 here unless there's a requirement for how I manipulate and manage the infrastructure host. So very often there is going to be that requirement. So we wouldn't necessarily just see a pure L3 here. We might actually have a customer who will use some VXLAN so that they can extend L2 for some connections, like that. The way our VMware Cloud Foundation operates, there isn't a necessity to extend L2 for various reasons in the management domain and things of that nature. And the workload domains don't need it so much, but the management domains definitely do. And how to communicate into those workload domains definitely does as well, as far as managing those workload domains from the management domain. So therefore, L2 extension is required. So we're going to see the fact that you're going to have some L2 extension in the racks anyway. So if you just wanted a pure L3, there could be some issue with doing so in the way we would want you to run NSX or VCF in this particular case. NSX itself wouldn't have so much the issue. It's really a VCF requirement.
VCF, yeah.
Okay. So pure L3, simplistic world. Why? Because it's stupidly easy, to be bluntly as honest as possible. It's just a routing protocol that sees every endpoint in some fashion from the end of a route, right? So an endpoint would just be at the end of a route, and it just means you have this massive sort of wide area network within your own little world there, if you will. Everything is just an endpoint off on its own little stub area.
It's literally stateless ECMP. It's literally pushing packets out as quickly as possible.
Yeah, and we recommend trying to use this as much as possible whenever necessary, because at this point, barring any yellows or reds showing up for something going wrong in one of your switches, right, you're not going to see any issue from the physical fabric. So if something isn't communicating and there's no warning of some sort in the physical fabric from some issue by your monitoring software and any of your visibility software telling you there's nothing there, then it's likely going to immediately scope to something within NSX. So at least it draws the focus a lot tighter to where the problem is plausible. All right. And vice versa. Obviously, if there was something going up, you can pretty much just bet that, well, if something went wrong and this thing's showing up bad here and one of your switches, you can pretty much bet that that's going to be an issue of concern to fix your problem.
Sure.
All right, so your mean time to repair begins to get scoped to a smaller time frame, just because you can immediately take some modest inferences when you're trying to scope the problem itself, not assume that that's the issue, but definitely begin to narrow where you might want to focus so that you can target it, and at that point then begin a resolution process. All right, determine the scope of the issue and things of that nature beyond the actual discovery of what is the issue. All right, so another L3 network, which is the more common one we're going to see, because it's going to be one that, as we noted earlier, we're going to require customers to use depending upon the nature of what you deploy from VMware. So if you deploy VCF, you're going to need some L2 extension. If you're going to deploy NSX, not necessarily so. All right. There could be just operational things because of some hybrid nature. You might want to extend L2 for some reason, but not necessarily so for many things, for most specific pertinent requirements for NSX. But let's assume you did have a desire to do it, and you just simply said, from the get-go, we're going to go ahead and at least afford us the ability to have it available. That's kind of a key phrase here. Per session.
There's a question: per session or per packet ECMP? We might need a little bit more specification there, Mohammed. Are you asking from an NSX standpoint and from an edge and how traffic is propagated out on our ECMP going out from the tier zeros? Or are you asking from the enterprise network, the underlay perspective?
If it's leaving the edges, it's going to be per session.
Yes, right, so, of course.
Yes, yeah. Okay, yeah. So, and if it's in the physical layer, well, it depends on how you set that up.
Yeah.
All right, and the capacity and capability. Obviously, it's per session just by the nature of it.
Most of them are session based and not packet based, to be fair.
Yeah, because by packet based, you begin to you get other cache issues that fall into play as far as how much performance can you push through on a packets per second basis using a per packet versus a per flow.
Per session, yeah, per flow.
Yeah. All right. So anyway, now we talk about flows. We're always talking about one way, right? Because we could have asymmetrical session connection. Yeah. All right. The other L3 technically, because it still is L3, and that would be the use of an overlay inside of the physical fabric. And obviously the one and only one that is today used in preponderance is VXLAN, right? Preponderance.
I've heard of it.
I've heard of it. Yes. So VXLAN then allows you to encapsulate traffic so that you can now have these L3 connections still. So they'll still persist. So underneath the covers, when you create the underlay network, all right, of the physical fabric, and then versus the overlay of your configuration, you'll have elements that are for the underlay and you'll have elements that are for the overlay of the physical fabric. We're not talking about NSX here at the moment. All right. You will have underlay elements such as the routed connectivity that we mentioned before. And then on top of that, you'll run an overlay setting so that you'll run network virtualized encapsulation interfaces off of these, or taps, physical taps on your switches, and you'll craft an entire TEP infrastructure and then create a de facto default virtual overlay of, inside of that environment, and then beginning mapping out VXLANs to VLANs. And at that point, then you can then say a specific VLAN gets mapped to a VNI, and then that VNI becomes your bridge identifier, so that you can then extend that bridged VLAN over to another system, another host, or another switch within your fabric, and that can be cross racks and cross rows, as well as cross sites. But we start getting into multi-protocol BGP, EVPN.
And yeah, we start talking about multi-protocol BGP with EVPN. And like what we're talking about here is with the NVEs, you're essentially using that as your data plane, and you can use BGP as your control plane with the multi-protocol BGP with EVPN. You can also not only use that for your host base or your control base, or you can also set up PIM and multicast to be able to then broadcast out your or be able to find your using your bum traffic. So there's a lot of different configuration options that you have there, but depending on what you choose, there's going to be a massive amount of configuration that has to be configured on every single one of those switches, and all the VLAN mappings and everything. You're manually going to have to allocate your VNIs to your VLANs, keep track of all of that to do all that layer 2 extension.
Yeah, and what we'll do is on the next session we'll come back is we'll look a little deeper into what that will require, so that we'll have like a part 2 of setting up that environment. And the reason we want to focus in on that is we want to try and show you that your going to still probably set that up to some extent, but we're going to try to get you to set less of that up. And we're going to show you the operational value of NSX, of running NSX virtualized environment over a physical infrastructure that is as simple as possible, so that the mechanics of your underlay is really very fast, high performant, static, if you will, not very little dynamic nature. Obviously there's routed services, but we're not adding much into that. We add new workloads. It's not adding new routes per se in the infrastructure, because the underlay itself is still seeing all of this through a single tunneled endpoint connection throughout the entire of the fabric, or at least a limited number of segments, of routed segments that our TEPs can provide of a necessity due to an L2 or versus an L3 desire within the TEPs. So that's another discussion in itself. But the idea being is we want to simplify this so you don't have to go through this magnanimous setup of trying to decide where L2 should be extended and not extended. If I use the same L2 VLAN value off of my TORs, because I've exceeded 4,000, how do I do more than 4,000 VLANs on a single TOR, just because there's a possibility that I could actually have an overlapping VLAN value, just because of the nature of my environment might just grow organically. And then that causes an issue, because you obviously can't do that unless your switch has the capability of actually seeing two distinctly different L2 value, or excuse me, L2 broadcast domains of the same VLAN value, but separate VNIs, because they're separate bridge domains inside of the VXLAN infrastructure. So you start seeing issues, as you could imagine, and complexity building in doing so, where we're going to show you, we wipe all that out. We're still going to want those same VLANs. So you're still going to have management. You're still going to have vMotion. All right, you're still going to have IP storage, and we'll just put IPS. Okay, so sure. IP storage, and then of course you're going to have your TEP, and then you're going to have your edge VLANs here too. So the edge VLANs will still exist. All right. Okay.
Yep, the VLAN backed, as we were talking.
All right, and then so you would still have like VLAN 10 here for this one, and VLAN 20 here for this one, for instance. All right.
Sure.
As your two VLANs. So the SVIs for the edge is going to be on that. And then there obviously could be, of course, two or more racks of those edges. And if it's a VCF infrastructure, these are probably going to be local to the domains themselves. So you'll have essentially edge infrastructure on a variety of rows, or racks, excuse me, within that row, as opposed to just something that looks to be just a border leaf within a smaller enterprise NSX infrastructure setup. All right. Yep. So that's why we got to probably spend a little more time on another session, and so we don't get too complex today in dealing with the makeup of that environment. But the VXLAN infrastructure at least allows us then to take and allow these TEPs to be available throughout the entirety of this environment. So this VLAN, this orange VLAN, okay. All right, so this orange VLAN is then available, if you will, extended through the VXLAN. So this VLAN value can be extended. The VLAN for the TAP can be extended. All right.
But I think it's also important to say that while this is an option, the TAPs don't need to be on the same layer 2. They can be layer 3 separated. As long as there's no firewall that's sitting in between them, it does not matter.
No. The only reason that you may wish to do so is if you've already set up this infrastructure with VXLAN. It could be one of the benefits of just extending it, or we could, as noted by Andrew, these could be separate L2 domains, and it could just be a routed infrastructure on a per rack basis. So that's fine to do as well. It's really up to
it's up to you how you built your network. I mean, the flexibility is there. We're not going to tell you exactly how to do it. You're able to do it either on the same layer 2, or they could be layer 3 separated.
All right. The main goal of what we're trying to do is that KISS principle. Let's keep this as limited as possible in complexing up your world. If we can use L3 here, then you're right. This could be separate per rack, a different IP segment for each of that. And it's a routed TEP architecture from our perspective. And we don't care, because it's a simple routed noded value that you're already addressing in the way you set up that underlay infrastructure. That's not going to change. That's still going to persist. It's just a matter of whether or not you had to carry an L2 bridged VLAN value through your VNI infrastructure in the underlay, or if you needed to, you could do so. So it's up to you to decide how you wish to troubleshoot it, because you always have to assume whatever you set up, you'll end up troubleshooting at some point, likely. Just assume you will. It doesn't mean it will break, but just assume you should always think of it. So the less I set up, the less I have to deal with that. And this is where we come into a huge value play, so that we get to why we're providing this. Whether this was that older legacy architecture or one of the two different leaf spine architectures, routed only, or a hybrid of some sort with VXLAN be playing a key ideal of setting up the leaf spine architecture here with obviously L3 links or an L3 environment with your VXLAN. The value is that once we create any of the segments, we create a logical segment here, and we haven't actually drawn it out the way that would truly look like in a much better representation. But once we do so, you're not addressing that structure up here. The endpoint resolution of these endpoints is done by the TEP inside of ESXi and NSX itself. NSX is playing that control plane knowledge of how to provide that endpoint resolution, and the data plane doing endpoint resolution, whether it's been resolved precedingly in some proactive fashion by NSX, because that's a whole other discussion of how NSX control plane operates, or it's done as a lookup at the time that the source of destination traffic is desired, and it comes up that the TEP doesn't have knowledge of it. Now it needs to, of course, do some reactive endpoint resolution. But NSX is dealing with this. The physical fabric is out of it, and it's completely automated. Whether you set it up with your TEPs being routed or L2 the same across, it's irrelevant. All of that is handled in an automated fashion. And we have a means of dealing with that automated fashion with one of two different ways of setting up that control plane traffic inside of the environment.
Which is massive time saving, because instead of having to worry about the VLAN to VNI mapping and worrying about the BGP and your control plane there and your data plane and setting up your NVEs and assigning those VNIs to those itself, and then putting a multicast, for the bum traffic. Well, you don't have to worry about all that on your underlay. Your underlay becomes very simple. It's a very simplistic design. And even if you want to talk about from the routing perspective of having your edges using BGP to connect off to the edges, let's say they're VM based and you wanted to expand your cluster to be able to have more to be able to use for throughput. If you want to even make it simpler, you can actually go into NXOS, let's say from a Cisco side, if those were Nexus switches, and you can do a BGP relationship that's based on a subnet range. And as long as you're keeping the same autonomous system numbers, which I'm going to assume that you are, and then you're not going to be changing that out. You can bring up a brand new, edge. You can add it to the cluster. You can bring up its interface, and then boom, BGP comes up, and now you have it added into there as an ECMP lane that can go in and out of your NSX infrastructure. So, there are ways to deal with. The whole goal is to keep this stuff super simple, so that you don't have to worry about the operational complexities, and you can focus on other things like meeting the needs of the application developers and expanding their applications and the infrastructure that they need. Whoa, right. That is one squeaky one line there.
And what Andrew is referring to is the fact that we can provide this distributed routed architecture that I drew out in our preceding discussion, so that obviously we would have our edge here, right? And this would be our T0, right? And then we'd have our T1. Both of those are actually elements inside of that kernel. So that that wouldn't be here. This would be, oh yeah, but there would be one. It depends on the nature of the fact. If it's a transport host, technically it still has it. It just doesn't operate there. It would operate inside of the virtual machine nodes themselves. So there would be a VM here. And then, of course, the VM itself would have that distributed route. And then the host here would have it. The idea being is that when we go back and we would draw these virtual machines now back the same way we just had it a moment ago, it conforms more so with the way we want to see it and visualize it. So that when these systems communicate, all right, remember we said that they're going to communicate and route on the distributed routed service within the kernel here at a very high performance rate, and they're going to switch over here at that same. There's no distinction. It's kind of like the same way that you could deal with, think of Cisco Ceph, right? Cisco Express Forwarding had that a means of not that has that mean had, but they still of course have. And
Sure.
I don't know what they refer to their algorithms today, but it's probably some offshoot of it. But the idea being it's essentially just a rewrite. So you're not really doing a lookup, you're just rewriting the headers of the Ethernet and IP headers if necessary for some modification of obviously what changes at the IP itself. But the idea being it's just simply a rewrite. You're not doing this control plane lookup through the data plane, through the control plane, because all that's cached and it's just a rewrite. And that makes it very high performant in the system. If it has to exit the system, obviously it's going to go through those links to the physical, and we're impacted by what other offloads we can provide so that we can get that near line rate of your 10, 25 and gigabit and higher. Obviously with SmartNICs, we'll be able to attain much, much higher performance, your 40, 50, and 100 as they come out for your SmartNICs. And then communication is this T1, as we note here, is the distributed services here. And then we also have essentially the T0 on these interfaces here, as we talked about when we discussed our original, I think it was our first telecast, or I was going to say telecast stream.
Telecast?
59. Give me a break.
I like it.
I lost a cell or two today since I turned 59. All right. Therefore, we just do a rewrite when we need to get out and exit out. And then through ECMP, the magic of it will dictate what other T1 will shuttle to whatever T0 service off of the edge itself. And then, of course, enter de-encapsulated from our Geneva environment into a VLAN-backed world. And if there's VXLAN in here, at that point, then that's fine. Your endpoint resolution operates from the fact that it sources whatever endpoint it sees at the routed service here as the endpoint as it comes out to the endpoint where it needs to be destined to, whether it's someplace within the environment through a DCI interconnect, or of course to some external internet connection of sorts.
Yep. And I think it's important. Like let's I know we've been repeating this over and over, but I want to really hammer it in. If there's one thing that you're going to remember when you walk away from this live stream, is that T1, that T1 DR and the tier 0 DR, that's in each one of those hosts. So if there is traffic that is on the orange segment going to the green segment there, and they happen to be on that same far left host over there, it's not going to have to route out in any way, shape, or form just to come back in. It's all going to be switched in the kernel. It's all going to be routed appropriately and then switched over to the VM. So everything's in there at near line rate.
Right. And the best part now is, where do you garner some huge value? Well, you can obviously do vast L2 broadcast domains, because that's what this represents. So, and this can be up to a couple thousand workloads on each of these broadcast domains. Or you can create another one. And it's literally as simple as drawing a line. The automation that we've allowed you and afforded you, that we're not going to get into today, but the automation capability we have today is that you can draw that line, and it essentially it's that simple from a consumption basis. And notice I do nothing here. Now, this line obviously represents another IP domain of some sort. Now, it could be natted so that it would be something that wouldn't get represented through a routed value on the tables at the edge here with your border leafs, or it would be one that would, and the way you have set this up, it just would be an automated value that would be grasped by the edge and therefore learned by your TORs. And at that point are the border leaves here through the EBGP communication. And at that point, then you would have it. So the only restriction you would have to concern yourself with is making certain there's no ACLs disallowing the knowledge learning of it. If not, that can be a step that can also be automated so that that can be added for allowance of that learned new route.
We have a very interesting question. Hello, why do I need a VNF third party to connect the EVPN Type 2 to my NSX environment? Are there any plans that NSX can do this by itself? I'm talking about the route server mode.
Well, in the route server mode, I'm trying to think of where he's looking at this from a use case perspective.
Well, probably extending the EVPN Type 2 into the NSX environment. And we're probably talking about either VRFs, and we're talking about multi-tenancy in some way, shape, or form. This is a a more advanced discussion than what we have drawn out on the board, I would definitely say.
Sven, I would like to have a little bit more clarity of why you are assuming that we have to have something in addition. We provide the ability to provide route server mode servicing through the NSX infrastructure. So when you say you need another VNF, a virtual network forwarding of some sort, what are you referring to that's requirement here? I guess I would like to have more clarity on what he's asking.
Yeah, and we can, if we don't have the answer today, we could definitely get you that answer. And you know what? There is actually a future show that I want to do, Sven, that is going to be purely around connecting EVPNs into the NSX fabric and actually showing it in a demo live. So that is coming up on a future show. We're doing the basics of it right now. So yeah, a little bit of a more advanced question into it, but I definitely want to touch upon that if we can get some more
Sven, and by the way, I wonder if your environment is a specific physical fabric that I'm thinking of that doesn't allow EVPN anyway at its edge. That would be strictly an L3 out of ACI. They don't allow not a VNF, EVPN connectivity, They don't allow EVPN connectivity on its L3 outs. Cisco's ACI environment is strictly proprietary. So the only way to do any type of VXLAN EVPN connectivity is through ACI. So customers can't use EVPN with ACI. They could with NXOS, oddly enough, which is still technically the OS that runs underneath it, but it's a specific OS version for ACI versus an OS for NXOS. So they refer to it as NXOS for ACI versus just NXOS.
Yeah, we would definitely need a little bit more clarity to be able to get you that answer.
Well, going back to what I wanted, because I don't want to keep jumping topics into something of a complex nature that we're not dealing with today, but let's get to, like you said, maybe that will schedule a specific service-oriented set of service offerings off of our routed communication that we can provide through NSX, and we can cover more complex topics like that. So that way we can do so at the right course, because it's really out of the scope of our discussion today, and it really doesn't afford us any value in this discussion. In this discussion here, the issue is that we just added another logical segment, and that logical segment has its own IP domain space. We can then allot for it, plan for it, and then consume it without having to do any extraneous effort in the physical fabric. And in fact, your apps people and your virtual infrastructure people could be deploying the apps themselves and using and consuming that new logical segment and its own IP address domain, and not have to concern themselves with contacting some SME, some subject matter expert, in order to facilitate its allowance. It was already set up to be allowed, and therefore when they go ahead and start enabling the workloads inside of that environment, and we refer to that environment for us as a VPC, but we're not going to cover that today because it's just, again, outside the scope. But the idea being is, even if I don't have a VPC, I just need NSX to go ahead and create that segment. And if I use the default settings, it's going to use a connected value for how its routes gets redistributed into the routing protocol, because as we noted in an earlier discussion, the T1 and the T0 use sort of an autostatic setup, so that whatever it's fed as far as a new IP prefix, it will go ahead and stream it into its upstream routed tables and go ahead and automatically advertise it if you so desire. You don't have to do that, but it is a setting that you can afford yourself to make it essentially a simplistic usage and consumption of new IP space if you so desire. Obviously, security concerns aside, these would be a means of just a minimal amount of operational overhead if you had some security restrictions on the addition of that new IP prefix for obvious reasons.
Yep. Meaning we have the ability to do IP prefixes. We have the ability to do redistribution, route maps, you name it, all the same things that you would normally see in a network.
Correct. And all of this can be done at that T0 edge, where the T1 is a very smart router, as opposed to old NSXV, which was essentially more of a traffic cop that could just say these IP networks connect, and it had no understanding of anything other than that. But it did also require you, though, oddly enough, to smartly configure the use of route protocols, whereas here it's very simple. It's kind of like you're in the cloud. I just add a new segment and it'll immediately feed that understanding up to the T0, and therefore the T0 will go ahead and include it in its advertisement, assuming that is a setting that you have permitted through its default and way of communicating that network. This then gives us that simplicity. It's why a lot of times you just see us drawing lines, the segments, because it's literally that easy.
But it's nice to be able to go through now that we've actually done it, just to show like, yeah, we simplify it, but we wanted to actually go through in this live stream and actually break down exactly what that line means and why we cut it back to be so simple. It's because it's meant to be so simple.
Right. And once again, the workloads and the endpoints themselves, they're all being resolved within the NSX kernel inside of the VMware vSphere kernel. So all of this is being taken care of in an automated fashion. There is no requirement to have any necessity to for the endpoints here, because the endpoint is still, from its standpoint, one of only a few. It'll be the TEPs themselves and the edge that the routing communication is coming off of. And the IP address, obviously, that's now being sourced out of a packet that's coming from the south going north or coming from the north going south. Those IPs, of course, would have to be dealt with by the physical infrastructure. But at the same point, we're doing all of the heavy workload lifting, and we're doing it in a fairly automated fashion where you don't have to do that work anymore. And this is why we have customers coming to us and installing, whether it's VCF or a VCF-like architecture. In other words, they stack the systems. They just don't use the prescriptive VCF alignment of purchasing that SKU. But what they'll do is they'll buy essentially the same element of that cloud structure, so that they have virtual SAN, so they have virtualized storage, they'll have virtualized networking, they'll have virtualized compute, and therefore the physical fabric is just providing that simplistic IP communication for those kernel elements, because that's all they are, right?
Yep.
And at that point, and then of course, any of the IO that comes out of a north-south basis. And if they're heavily virtualized or moving toward that, this becomes ideal, because this is simple. This is repeatable. This is just add another rack once I require the use of another rack for capacity and scale out, and I begin to build out what that rack will consume. Or if I'm building it out because I know there's going to be so many alignment of hosts within a row, I build out the row in a more service provider perspective, and then the racks get consumed, and I just go to another row. But the case being is this is idiot proof, and this is really very simple, and that is the value of that. It can't be any more simpler than that, because the physical fabric didn't change. I can add 1,000 workloads. I can go to 10,000 workloads. And assuming that the nature of that workload communication is still largely scoped to the virtual fabric itself of NSX, as far as its east-west needs, so that'd be load balancing, security servicing of any kind from L4 through L7, load balancing of any kind, L4 and L7, ingress and egress from any of our cloud-native workload deployments, so it's Tanzu of some sort, right? Or OpenShift even. All of that is managed and manipulated inside of the virtual infrastructure. The physical infrastructure largely stays static, resilient, and high performant. Those are your three big concerns, which means you really lose, you really only have then the concerns of keeping those switches based upon only a few issues. One, is the switch still supported?
Yep.
In other words, does the vendor actually offer you updates to that switch? Because obviously that would cause it to be. Two, did it break? Obviously that'd be a problem. And three, is it giving you the IO?
Yep.
If you meet those three simple needs, all right, then this switch infrastructure can last as long as probably the first one, the other two, right? The other two being the issue of support, as well as it's not broken.
Yep. Well, Paul, you know what? We went really long today. This was great, but I think we hit a lot of great topics. I think we hit the history. We looked at a couple different network architectures, from the core distribution access, going over into the more modern CLOS and looking at VXLAN on your enterprise network, how it all connects in. We talked about routing protocols. We talked about the edges, tier 0s, tier 1s. We went through a plethora of things. So I'm really happy with how this turned out. We had some great questions, and I invite everyone to come back next week, because we're going to have another continued session on this. We're going to do even more. We're going to get into a little bit more of an in-depth topic. If I remember correctly, Paul, we're going to be talking about a little bit more of disaster recovery and federation, right? Correct?
Well, I think we wanted to do a part 2. I thought with this
We
one.
can do a part 2 of this. Actually, I mean, that's how flexible we are. I think
Yeah,
a lot of people.
Part 2 of this, and then I think we'll come back to that because I'd like to just do a little bit more of diving into some of the elements of what we can provide on this. Or as you said, I think it just would be very helpful. Also, I would like to get back to that virtual network function that issue the gentleman was referring to.
Sven just replied. Wow, it's funny. He goes, I wanted to connect my EVPN BGP VXLAN from the hardware environment into NSX to get the layer 2 from my data center into NSX. I wanted to do this because of multi-tenancy reasons. So I was right about the multi-tenancy there. As far as I know, this is doable from the NXOS standpoint.
Yeah, I'm wondering what version of NSX you're running into and what EVPN type issue that is causing this problem. I know you said type 2, but I'm trying to think of why we.
I'm wondering, is this an
because
ACI
there's a type 2
like
versus a type 5 issue could be the problem. Is Sven still there? Obviously he is. I guess he just typed in that question.
He's going to watch for the following sessions. I'll tell you what, how about this, Paul? Let's you and me go back and let's plan a session around this and let's talk about this specifically, because I think there is, especially from a service provider or a multi-tenancy standpoint, this is a pretty popular topic to talk about. So Sven, we are going to follow up with you and we're going to bring up something like this.
Well, he also could be a telco. I mean, there's a
Definitely
whole telco usage with that particular aspect.
Okay. Yeah. So, all right, we're going to do part 2 next week. I think on, Wednesday. I know that we were going to do this Wednesday last time, but ended up we weren't able to do it. So we had to move it back to today. But next week, we're planning on Wednesday at 2:30 p.m. Eastern time. We're going to do a part 2 of this. Sven, we're also going to talk about, I'm going to put on the show in the coming weeks. We're going to figure out something that Paul and I will talk about multi-tenancy. And we'll hopefully have some kind of live demonstration that I can show you. I think I can build something up in my lab. Paul, any closing thoughts before I do the wrap up?
The 2 things. We're agnostic to the physical infrastructure. I think that should be noted. And when we talked before, this didn't change. So regardless of whatever happens here or whatever entails future changes to the way the physical fabric would operate to some extent, for us, we're still going to come back to a simplistic requirement from that fabric and maintain a desire to keep it simple as long as possible with very minimal amount of operational overhead as we load the NSX network environment with workloads. And as we then talk later on, is one of our concerns, as Andrew noted, is multi-site and federation. So we're obviously adding NSX domains and management of those domains. That becomes more of our concern versus worrying about the concern of managing the load of a single NSX domain, because that's fairly feasible and simple operationally from a physical as well as an NSX perspective.
Oh, Muhammad actually had a really good question really at the very end. Are there any good resources we could recommend? Well, I know TechZone has a tremendous amount of information that is there. So TechZone, is it what, nsx.techzone.vmware.com or is it techzone.nsx? Let me just nsx.techzone.vmware.com. We also have these live streams like I was telling you about. Obviously we're doing this every week, or we're trying to do it every week. On top of that, we have, the configuration guides that are out there are tremendous areas to go to. Let me actually try to quickly bring up nsx.techzone. Yeah, there we go. I'll put that link here into the chat right now. That has a tremendous amount of information that you can find there. The configuration guides, the administration guides, all that we have. Those have tremendous amount of information as well. VMware Explorer just happened. We have a ton of those videos that are all on demand that you can see. A lot of great sessions, a lot of great in-depth discussions. We were all kind of a part of it and developed the material. So we're happy for you to be able to join in and take a listen to everything that we had to say. Paul, any other additional areas you can think of?
No, I think all we're doing is extending our time. So
yes. All right. Well, Paul, I'll see you in a second. Hang on the line here. Ladies and gentlemen, thank you so much. I want to thank Paul Mancuso for once again coming in on the live stream and doing a fantastic demonstration of everything that was going on. He does a great job on the light boards. He does a great job on explaining these things very simply and easily. We love taking your questions. We're going to make sure that we meet some of these, questions that were coming out of, multi-tenancy. We're happy to hit on those things, and we're going to do some more live, demonstrations there. So thank you so much for joining. We will see you next week on Wednesday, 2:30 p.m. Eastern Time. Have a great day. See you later.